In this video, we are looking at number system. Start from natural numbers. Natural numbers include 1, 2, 3, 4, 5, 6, and so on. You can continue. How many natural numbers do we have? Infinitely many, right? You can keep going, keep going. The smallest natural number is 1. They are all positive. All the natural numbers make a set. The set is called the natural number set. Whole numbers include 0, 1, 2, 3, 4, 5, 6, 7, and so on. So there are infinitely many whole numbers. The smallest whole number is 0. We got a whole number set by adding 0 to the set of natural numbers. So you can see the connection between the two sets. Natural numbers are whole numbers. Natural numbers are part of whole numbers. Whole number set is bigger than natural number set. When this happens, we say natural number set is a subset. There's a concept here, subset. All the natural numbers make a set is a natural number set. All the whole numbers make a set. We call the set whole number set. Natural number set is a subset of a whole number set. So maybe I can show you, let's say, if we put all the women together, female, we have a set, right? Set of females. And this bigger one is the set of human beings, humans. All the females are human beings, but a human being might not necessarily be a female. So the set of female is a subset of the set of human beings. The same with these two sets. Natural number set is a subset of a whole number set. Integers. Integers include all the whole numbers, also the opposites of the whole numbers. Let me show you what is the opposite. 0, the opposite of 0 is 0. 1 has the opposite -1. Just change the sign in front of the number to the opposite sign. Positive becomes negative. So -1 is the opposite of 1. This word opposite. Opposite. -1 is the opposite of 1. 1 is the opposite of -1. The two numbers add up to 0. -1 and 1 add up to 0. They have the same numerical power, but opposite sign. 2, -2. 3, -3. 4, -4. And so on and so on. So you can see integers. You can see there are infinitely many integers here. All the integers make a set. We call the set integer set. Integer set has 0, has all the whole numbers as members. Also, the opposites of those whole numbers. So integers include 0, plus minus 1, plus minus 2, plus minus 3, plus minus 4. So you might already see that whole number set is a subset of integers, of the set of integers, because all the whole numbers are members of integers. Rational numbers. This concept, we're gonna spend time to really understand what is a rational number. What is a rational number? We are going to see two definitions for rational numbers. The first definition: any number which can be written in a form, any number which can be written in the form of P over Q. P and Q are integers. We have just learned what is an integer. Integers. The denominator Q has to be non-zero. Denominator is non-zero. It's kind of like a common sense in algebra. So this is the definition for rational number. Any number which can be written in the form of P over Q, where P and Q are both integers. The denominator, integer Q, is non-zero. In other words, any number which can be written as a quotient of two integers is a rational number. All the rational numbers put together make a set. We have the rational number set. Let me repeat the definition of a rational number. Rational number is defined as a number which can be written as a quotient of two integers. Of course, the denominator integer has to be non-zero. I'm going to write some numbers and you determine, you tell me which of them are rational numbers, which of them are not. 0, 5, -3, 1 over 2, -2 over 3. Okay, so just those 5. Let's see. Is 0 a rational number? We know 0 is a whole number. 0 is an integer. But is 0 a rational number? By the definition, you might answer is not, but 0 actually is a rational number because 0 can be written as 0 over 1. If you want, you can write 0 as 0 over 2 or 0 over 3. 0 is able to be written in the form of P over Q. So 0 can be written as a quotient of two integers. The bottom integer is non-zero. So 0 is a rational number. What about 5? We know 5 is a natural number. 5 is a whole number. 5 is an integer. But is 5 a rational number? By the definition, if we can write 5 as a quotient of two integers, then it is a rational. And we actually could do that. We can write 5 as 5 over 1, right? We can write 5 as 5 over 1. Then 5 is a rational number. So I mean, yes, 0 is a rational number, 5 is a rational number. Next one, negative 3. We know negative 3 is not a natural, is not a whole number, but is an integer. Negative 3 is an integer. Is negative 3 a rational number? By the definition, if we could write the number as a quotient of two integers, then the number is a rational number. We could write negative 3 as a negative 3 over 1, right? So negative 3 is a rational number. Next one, half. Half is a fraction. Yeah, it's a quotient of two integers. Top 1, bottom 2. So it is a rational number for sure. Negative 2 over 3 is a negative fraction. And we could actually write this fraction as negative 2 over 3 or 2 over negative 3. You can see the location. Where do I put the negative sign? The negative sign in front of the fraction could be moved in on the top or moved on the bottom. They are all the same. So you can tell we could write negative 2 over 3 as a quotient of two integers. Negative 2 over 3 or 2 over negative 3. that make -2/3 a rational number. So they are all rational numbers, right? Yeah, also you probably already see that integers are rational numbers. Integers, 0 is a rational. 5 represent any positive integers. They are rational numbers. -3 is a negative integer. Actually, all the negative integers are rational numbers. I mean, integer set, the set of integer is a subset of the set of rational numbers. Integer set is a subset of rational numbers. So that's the first definition for rational numbers. All the rational numbers, which can be written as a quotient of integers, can also be written as a decimal. For example, 0, you can write 0 as a 0.00, right? You can write 3 as a 3.0. You can write -5 as a -5.0. You can write 1/4. We know 1/4 is a 0.25. And you can write 1/3 as, if you have a calculator, you divide 1 by 3, you will see 1/3 is 0.333 forever, right? If you have a -1/3, you have a -0.3333 repeating. In fact, any rational numbers, if you convert the rational number to a decimal, how do you convert? You use the numerator to divide by the denominator. You will have a decimal. And those decimals are either finite, terminating decimal. So let me write here, rational numbers are terminating decimals. Or actually, I want to change this word to include. Include. Rational numbers include terminating decimals. What is terminating decimal? Let's look at 0.25. If we have a finite number of digits to the right of the decimal point, then that decimal is a terminating decimal. It means it doesn't go forever. 0.333, that is non-terminating because the 3 goes forever. There are infinitely many integers to the right of the decimal point. So 0.333, 3 repeating, that is a non-terminating. Rational numbers include terminating decimals, like 0.25. Even you have a million digits to the right of the decimal point is still terminating. And non-terminating, but repeating decimals. -0.333, 3 repeating. That decimal is a non-terminating because it goes forever, right? But it's repeating. 3 is repeating. There's a pattern for the decimal, for the digits, for the numbers to the right of the decimal point. We actually have a way to write non-terminating but a repeating decimal. For -0.333, 3 repeating, we can write it as -0.3, 3 repeating. We write a bar, horizontal bar. We put a horizontal bar above 3. That means 3 repeating forever. Turns out any rational numbers are either terminating decimals or non-terminating but repeating decimals. That's the second definition for rational numbers. The first one, rational numbers as a fraction. The second definition, rational numbers as decimals. So let me change the color here. If you see a terminating decimal, then that is a rational number. If you see a non-terminating but repeating decimal, that is also a rational number. So that's how do we define a rational number as a decimal, Terminating decimals, non-terminating but repeating decimals, they are rational numbers. So this is how do we understand rational numbers. It is more complicated than natural number, whole number, and integers. And so far, let's look at those number set. Natural number set is a subset of whole number set. Whole number set is a subset of integer set. Integer set is a subset of rational number set. At a certain point in the history of the development of number system, our ancestors, those mathematicians, they found a fact. They found a fact. For circles, it doesn't matter the size of the circle. For any given circle, the ratio of the circumference and the diameter. What is the circumference? Circumference of a circle is the distance around the circle. The ratio of the circumference of the circle and the diameter. What is diameter? This is the center of the circle, right? Diameter is the length of this chord. This chord passing through the center. This is the diameter. So no matter what's the size of the circle, the ratio of the circumference and the diameter is a constant. So our ancestors, they found out this, they found this fact. Bigger circle or smaller circle, no matter what size of the circle, the quotient of the circumference and the diameter is a constant. And that constant is not a rational. It is not a fraction. It cannot be written as a quotient of two integers. It's not a terminating decimal. It's not a non-terminating but a repeating decimal. It is a non-terminating, non-repeating decimal. It is 3.14. And so on and so on and so on and so on. So, yeah, that is pi. C over D equals pi. So actually, this story can help you to remember a formula. C equals pi d. The circumference of a circle equals pi multiplied by the diameter of the circle. Pi is a constant. This constant pi is not a rational because it's not a terminating decimal. It's not non-terminating repeating decimal either. It is a non-terminating, non-repeating decimal. We call that kind of decimal irrational numbers. So irrational numbers are defined as non-terminating and non-repeating decimals. So if we say a person is irrational, means there's no pattern to track. You don't see the pattern. Irrational numbers kind of like that. there are infinitely many digits to the right of the decimal point, and there's no pattern for those digits. So now we know pi is an irrational number. So if you have a calculator, you would be able to find a pi on your calculator. Besides pi, you will also see a letter E. A letter E represents another important irrational number. It's about equal to 2.718. That is also irrational. So pi and E, both pi and E are important irrational numbers. Besides those two irrational numbers, root 2, root 3, root 6, root 10, and negative, root 17. So those square roots or even cube roots, those radicals are also irrational numbers. We have infinitely many, uncountably many numbers. If we convert those numbers as decimal, those decimals are non-terminating, non-repeating decimals. So those are irrational numbers. Just to let you know, we have infinitely many, uncountably many irrational numbers. You might wonder, do we have more rational numbers or do we have more irrational numbers? So when we say rational number, we say we have infinitely many countable, infinitely many, but countable, many rational numbers. Countable means we are able to count those 1, 2, 3, 4, even it takes forever, but we are able to count them. However, for irrational number, we have infinitely many and uncountable many irrational numbers. So many, and we even not able to count them, like list them one after another. So just to give you an idea, how many rational numbers do we have and how many irrational numbers do we have? So now we have a question. What's the connection or relationship between rational numbers and irrational numbers? Do the two sets, rational number set and irrational number set, overlap? In other words, do we have a number which is rational and irrational? The answer is no. The two sets, rational number set and irrational number set, are disjoint. Joint, yeah. So means they do not overlap. Yeah, make it simple. Disjoint means rational numbers and irrational numbers do not overlap. If a number is rational, it's definitely not irrational. Vice versa. If a number is irrational, then it's definitely not rational. And all the rational numbers and irrational numbers put together make a set. We got a real number set. So here, how do we define real numbers? Real numbers include all the rationals and irrationals. Real numbers include all the rationals and irrationals. That is a real numbers. So all those numbers we have seen so far, they are real numbers. It includes, real number set include all the rationals and all the irrationals. So here I'm going to draw a diagram to show you the connection, the relationship between those sets. This is natural number set. We put a 0. We added one more member, 0. We have a whole number set. And if we put more members, if we include in the opposites of whole numbers, we have integer set, integers. If we include the quotient of two integers, we will have rational numbers. Rational numbers with irrational number. This blue region represents irrational numbers. And the yellow region, the biggest circle, this yellow region, represents the rational numbers. Obviously, they do not overlap, right? They are disjoint. So they put it together, make a set. That set is real number set. Real number set. So all the numbers in the rectangle, those are real number set. So this diagram, I hope it could help you to understand the relationship between those number sets and also the structure of the number system. Graphically, we could use a real number line to represent real number set. And what is a real number line? If we have a straight line, it could be horizontal or vertical or slant, it doesn't matter. Let's say most of the time we use a horizontal straight line, this straight line. If the straight line has 3 components, if the straight line has directions, if you determine this is a positive, this is a negative, if the straight line has directions, positive, negative, and the straight line has a origin, 0, and number 3, you determine and the unit of 1 is determined, then the straight line is a real number line. In other words, if we determine 3 things for a straight line, then the straight line can be a real number line. Direction, number 1, direction, number 2, origin, number 3, how much is unit 1? You let this much as unit 1 or this much as unit 1. So in other words, a straight line with 3 components, number 1, direction, number 2, origin, number 3, unit, then that straight line is a real number line. Real number line is the geometric significance of a real number set. So the 2 things are the same thing in different forms. In fact, there is a one-to-one correspondence between the real numbers in real number set and the points on a real number line. Let me explain what do I mean. So let's say we have a real number line. This is a 0. This is a 1, 2, 3, 4, 5, 6, 7, and so on. It's a -1, -2, -3, -4, -5, -6, -7, and so on, right? So this is a real number line. How many points on a real number line? How many points on the line? Infinitely many, uncountably many points. The number of points on the real number line is the same with the number of real numbers in a real number set. There is a one-to-one correspondence between real numbers in real number set and the points on the real number line. It means for any real number, there is exactly 1 point on the line corresponds to it. So for example, you tell me where is a half? Half is between 0 and 1, right? If you ask me where is the negative pi, that is a -3.14, is about here. So for any given real number, there's a unique point on the real number line corresponds to it. Vice versa, for any point on the real number line. There is only exactly one real number in the real number set. Make a pair with it. For example, when you see this point, you know that's number 7. When you see this point, you know that's number -1. When you see this point, you know that's number 0. When you see a point halfway in the middle, right in the middle of 4 and 5, you know that point is number 4.5. So what I'm saying is the two things are actually the same thing in different form. The point on the real number line is the geometric expression of real number. Real number is the algebraic expression of a point on the real number line. So sometimes we don't make a difference. When we see a real number, we say that's a point. That will be a point on a one-dimensional space on the real number line. When we see a point, we know that's a real number. That's a real number. So this is about number system. Important thing is you understand this diagram, the structure of the number system, of a real number set. Also, try to make sense of one-to-one correspondence between real number set and a real number line. Thank you for watching.